Welcome to Ask and Learn.
So the differential equation that we're going to solve here is x times y prime equals x squared plus 1. This is a first-order differential equation. The derivatives only appear up to first order in any of the variables in this equation. There are no second-order or third-order derivatives here, so it's a first-order equation. And it is separable, meaning that the x factors and terms will be able to be separated over to one side of the equation, and the y factors and terms will remain on the other side of the equation. This will allow us to apply separation of variables in order to solve the equation. Now, to get started, let's rewrite this equation in Leibniz notation. So we get x times y times dy dx equals x squared plus 1. Leibniz notation is very convenient with separation of variables, so we're going to stick with that for this exercise. Now, to begin the process of separating the variables in this equation, what we're going to do is divide both sides of the equation by x. That gives us y times dy dx equals x squared plus 1 over x, with the end result being that all the x factors and terms are over on the right side of the equation, and the y factors and terms are on the left side of the equation. Now, the next step here is to rewrite this equation in differential form. What we're going to do is to multiply both sides of the equation by this differential dx, so to speak, giving us y times dy equals x squared plus 1 over x dx. It's not exactly rigorous, but it is a convenient framework for applying separation of variables, and it does give us the correct answer in the end, which is the most important thing here. The only thing to keep in mind is that this derivative, dy dx, is not actually a quotient. Now, the next step here is to integrate both sides of the equation. So the integral of y dy equals the integral of x squared plus 1 over x dx. And it's critical here that we were able to isolate these variables onto one side of the equation over the other, because that's what allows us to do these integrals on each side. Now, the integral of y dy is very straightforward. It's just y squared over 2. And we're going to have to add a constant, but we'll do that on the other side of the equation. The integral of x squared plus 1 over x is also not so bad. It's just going to turn out to distribute over this numerator, so we get x squared over x plus 1 over x dx, which is equal to the integral of x plus 1 over x dx, and the integral distributes over the sum, so we get the integral of x dx plus the integral of 1 over x dx. The integral of x dx is just x squared over 2. The integral of 1 over x is the natural logarithm of the absolute value of x. And now we're finally going to add a constant. So now that we've evaluated this integral, what we can do is bring it over to the right-hand side of this equation and get x squared over 2 plus ln of the absolute value of x plus some constant c. Now we can multiply both sides of the equation by 2 and get y squared equals x squared plus 2 times ln of the absolute value of x plus 2 times c. Now 2 times some constant is really just some other constant, so it's not really necessary to go to the trouble of renaming this thing. We're just going to call it c again. Now the last step here is to take square roots of both sides, so that gives us y is equal to plus or minus the square root of x squared plus 2 times ln of absolute value of x plus c. And that is the solution.